Good afternoon, and thank you for the opportunity to present this work. My name is Anastasiia Senyk, and I'm honored to present our research, context-aware lexical stress prediction and phonemization for Ukrainian TTS systems. This work was conducted in collaboration with Mykhailo Lukianchuk and Valentyna Robeiko from Taras Shevchenko National University and Yurii Paniv from the Ukrainian Catholic University. And today, I will walk you through our modular preprocessing framework for Ukrainian TTS systems, which tackles two main linguistic challenges, phonemization and lexical stress prediction. So, high quality text to speech systems rely heavily on linguistic preprocessing, and this becomes even more critical when we work with low resource language like Ukrainian. So, in our work, we focus on two core steps: phonemization, a process of converting written text into sequence of phonemes, and lexical stress prediction, which is a process of identifying the correct syllable um, to stress in each word. Both of these steps are simplifying the path of learning from text to speech in a model to produce more natural and correct sounds. Although text-to-speech technology has advanced rapidly in major languages like English, Ukrainian has its own challenges that makes this direct adaptation of similar methods more difficult. First, and the main one, that Ukrainian is low resource language, and there are still a few high quality tools and data sets and pronunciation dictionaries which are freely available. Additionally, linguistically, Ukrainian has rich inflectional morphology, which leads to a large number of word forms. For one meaning, it has flexible word order, which affects both syntax and meaning. It also has other different alterations, assimilations, cluster reduction, and etc. Another challenge is unpredictable and lexical stress pattern. It the stress placement in a word can change depending on the grammar, context, meaning, and in many cases, there are words that could exhibit several possible stress patterns, and even the meaning of the word can change depending on it. For example, zamak as a monk, meaning castle and lock in Ukrainian, have the same spelling but pronounced differently and have different meaning depending on stress. And because of the combination of these factors, Ukrainian TTS requires more advanced and linguistically aware preprocessing to be able to generate natural sounding speech in TTS systems. Let's move on to discuss each of the steps. I will start with grapheme to phoneme or phonemization step. And though solution for other languages now leverages different approaches from statistical models to neural models like LSTMs, transformers, most existing Ukrainian GTP systems rely still on handcrafted rules. These are mainly because of two reasons. First of all, we have a scarcity of high quality pronunciation data that are needed to create more advanced methods. And another reason it's Ukrainian has relatively consistent and transparent mapping between graphemes and phonemes in Ukrainian orthography. Um, our phonemization method takes into account the context of the word, is context inside the word. It uses a rule, regex rules, left context, some grapheme sequence, and right context to map it to the correct phoneme sequence. We use EPA based symbols. In general, it's 52 symbols for mapping. Additionally, as other existing methods often have either overgeneralized rules, it requires manual input from the user, and it has poor treatment of assimilation and other methods in Ukrainian. We decided to create our own system, which is implemented in Python and using the sequentially applied regular expression-based rules. Each rule addresses own phenomenon from just basic mapping and this graph to other assimilations and consonant cluster reduction, consonant assimilation, sibilant assimilation, and other steps as we can see on the table. Additionally, as we have this fixed rule order, it ensures stability and interpretability of our approach. Let's move on to the lexical stress prediction system. And as we already discussed, it's crucial that our model understands the context of the sentence to be able to correctly disambiguate some stress patterns for words which have some ambiguous possibility of stress placement. And additionally, it's important that our systems works and identifies correctly the stress patterns for out of vocabulary words, as real world input often has some typos and different neologisms are formed as language developed through the time, and additionally vocabularies are limited and does not have each of the spoken rules. And while there's one existed method, accenture transformer, which takes into account context, it only partially support out of vocabulary word, as its training data was derived from some fixed dictionaries based on Ukrainian word stress method, and it often fails to predict any stress for unseen or ambiguous words. Additionally, other method, as Ukrainian word stress, is based on the dictionary, and Ukrainian accenture operates only on a word level input. To support the evaluation and comparison, we created the first sentence level Ukrainian stress benchmark. We included the sentences from Wikipedia and graph corpus, which covered diverse writing styles. Each of these sentences were cleaned and manually annotated with stress labels by the native speaker, and to improve the ambiguity coverage and how a lot of words which are in our benchmark in both forms, we added our custom edition of almost 300 sentences, and we reached in the end that in our benchmark totally over 1,000 sentences and almost 300 words which appeared in both stress form in our benchmark. This data set we used as a foundation for evaluating different lexical stress prediction systems in real world context. As for the lexical stress model, we adapt a multi-stage pipeline inspired by Geneva 2023 paper. And since there is no suitable data set existed for training, we decided to create a synthetic one, which was derived from automatic speech recognition tasks. We augmented the ISR data with stress labels, trained the model, and we annotated the Voice of America speech corpus. This data was then used to train our sentence level by the 5 GTP model for stress prediction. As for the RSR model, we selected WOW2WEC2 and trained it on common voice dataset using already existed tools for synthetic data. It's Ukrainian word stress, and we used Ukrainian accent for the fallback. So I'm ready to present our empirical results on both tasks. Starting with phonemization, we evaluated our GTP system using two data sets. Both was reviewed by expert linguists, and the first data set contains under 500 manually selected words. It was designed to cover a wide range of phonemes, but excluded different controversial cases. And the second data set includes more than 550 words automatically extracted from Western dictionary, which exhibits more challenging examples like proper names and different rare forms. We measured performance using word error rate, and on manual dataset, our system achieved 1.23%, on automated 3.07%, and on automatically generated dataset using this additional controversial cases, it achieved 6.15%. And in contrast, our baseline system, which is just a simple letter to sound mapping, reached almost 50% of word error rate. As for the lexical stress prediction model, our BT5 GTP model outperforms its baseline of neural models, Ukrainian accentor and Ukrainian accentor transformer, and it nearly matches the results of dictionary-based Ukrainian word stress system. And as its contextual disambiguation is strong, is limited now by a sparse heteronym coverage in the training data, and also reliance of automatic labels in training data set. But the best results comes from a hybrid approach combining dictionary-based Ukrainian word stress system with a fallback to our model for cases where it was not possible to disambiguate with just a standard system. So, to summarize, we propose a modular pipeline for Ukrainian TTS preprocessing, which combines a rule-based phonemizer and BT5-based lexical stress predictor, which was trained on pseudo-labeled sentence data. The rule-based phonemizer achieves 0.23% of word error rate, and our stress predictor reached state-of-the-art performance for neural baselines and approached dictionary level accuracy. Additionally, we released the first public benchmark for Ukrainian sentence level lexical stress prediction. And also there were several key directions ahead. As for the lexical stress model, there one way to enhance heteronym coverage in training data, or additionally use a manual labeling of the training data set to ensure more accurate training data. And as for phonemization, to extend our approach to a sentence level processing, as our method now only supports a word level input, and additionally it's possible to add the support for abbreviation and different numerical expressions, and also adapt for different dialects and informal language of Ukrainian. So that's all from me. Thank you for thank you for your attention, and bye.